Hi, welcome to this lesson on number patterns, geometric sequences. Firstly, what is a geometric sequence? Let's have a look at the definition. A geometric number sequence is an ordered list of numbers that follows what we call a multiplicative pattern. What does that mean? Well, start with a first term, which we will call A. And to get to the next term, we simply multiply each previous term by a constant value r, which we call the constant ratio. Mathematically, we denote any geometric sequence in general by this formula. T sub n equals a, which is your first term, times r, which is your constant ratio, raised to the power n minus 1, for all natural numbers n. But where does this formula come from? Let's have a look. We said to get the general term of a geometric sequence, we observe the following. We started off with the first term a. Let's call that t sub 1, which stands for the first term. To get to the next term, t2, we said that we multiply the previous term by the constant ratio r. In this case, the previous term, t1, was simply a. So we multiply by the constant ratio r to get a times r. To get the third term, we simply take the second term, which is the previous term, and again multiply that by r to get ar times r. But these r's are the same base, so we add their exponents. They both have an exponent of 1. So 1 plus 1 is 2, and therefore you get ar squared. Next, to get the fourth term, we simply take the previous term, which is the third term, ar squared, and again we multiply that by r. So all we're doing is taking the previous term and multiplying it by r to get the next term. So t4 would be ar squared times r. Exponential laws tell us, because r is the same base, we add the exponent of 2 here, and this has an exponent of 1. So 2 plus 1 is 3, and that is where we get ar cubed. The cubed is acting on the r, the constant ratio, not the a. It is only acting on the r to the power 3. That is being multiplied by a. So in general, we can notice a pattern happening here, and that is the beauty of mathematics. We look for these nice patterns. So from the observation, I see that if I look at the position in the sequence, the first term, the second term, the third term, the fourth term. So if I listed them out in order, first term, second term, third term, fourth term, so on until I get to the most generalist term, what does that look like? In the first position, which is the first term, it is just a. In the second position, it is now a times r to the power 1. In the third position, it is now ar squared. In the fourth position, it is ar cubed. So, what is the pattern here? Well, if I look at the position for 2, 3, and 4, I see that the constant r value, the power, seems to be 1 less than the position that I'm in. So first let's note, every single term has an a in it. A. So they definitely all have an a. Then they have a times by r. But the power of r depends on the position of the term in the sequence. At the second position, or the second term, the power is 1. At the third position, the power is 2. At the fourth position, the power is 3. So in general, in the nth position, so this denotes the nth position, the power of r simply seems to be 1 less, n minus 1. And that is where we get the general formula for a geometric sequence. What about the first term, you say? Well, if we plug in n equals 1 here for t1, we get a times r to the power 1 minus 1, but 1 minus 1 is just 0, so I get a times r to the power 0. But we know any non-zero base to the power 0 is what? 1. So that's going to be a times 1. An exponent raised to the power, base raised to the power 0 is 1. And a times 1 is just a, which is the first term here. So this is the general formula for a geometric sequence. So whenever you are doing any problems relating to a geometric sequence, this formula here must come forefront in your mind when solving the problem. The key variables to know are the first term a and the constant ratio r. Alright, we're going to discuss some more properties of the geometric sequence next. I'll see you in the next one.